Now the next one we're going to learn is to derive the formula for the combination of resistors in series. So series means you put them this way, so this is called series. So how do we find the total resistance in this circuit if you connect them in series? Now to derive the equation, we will start from Kirchhoff's laws. So we're going to start off from Kirchhoff's second or first law. I'll teach you what to do. Now first you need an equation that shows that something of this plus something of this plus something of this must add up. So when you connect them in series, what do they have in common? Shalvin, what do they have in common if they're in series? Current. Well done. So the current is constant, so we cannot add the current here to here to here, but what we can add is the voltage or the PD. You understand? And remember, we learned about Kirchhoff's second law as well. The PD here plus PD here plus PD here equals to total PD, right? So that's what we start off with. Okay, so from Kirchhoff's second law, because we need an equation, something equals to something plus something plus something, so you'll be adding the voltage. So the V total equals to V1 plus V2 plus V3. Now remember the formula that V is equals to IR. Now why I want to change it? Because I want to change the expression from voltage to resistance. Alright, so therefore I change this to IR. So the total voltage here is the same as the total current I, alright, times the resistance R total equals to IR1 plus IR2 plus IR3. So why is it the same current? Because they are in series. And how do I know it's the same current? That is from Kirchhoff's first law. Because Kirchhoff's first law tells you that if there's a junction, it will split, right? But there's no junction, so it's the same current. Right, so now you notice that we can cancel the I, and that's how we get our final formula. Alright, which is whenever you connect them in series, the total resistance is just adding up all of them. That's it. No special formula. What about resistors in parallel? How do you get the formula? So for the purpose of our discussion, we can also draw a cell here, so to help you understand. So let's say there's a cell here which has an EMF of V. Okay. Now when you connect them in parallel like this, what will be the same for each of them? Voltage. Okay, so voltage will be the same, but what will add up is current. So remember, we must start with an equation, something equals to something plus something, right? So we start from Kirchhoff's first law, and we we look at this junction here. Okay, the total current equals to I1 plus I2 plus I3. Now remember, our objective is to find the expression for resistance, so therefore we need to change the I to R by using this relationship. But since they are in parallel, that means the total voltage here is equals to this, equals to this, equals to this voltage also, right? So therefore, from Kirchhoff's second law, the total current is V over RT equals to V over R1 plus V over R2 plus V over R3. Then you can cancel this, and finally you will get the formula for resistance in parallel. Now the next thing we want to talk about is how did we use the Kirchhoff's second law to prove that all of them have the same voltage. Why all of them same voltage? Because you can take one loop this way, and remember the EMF must be equal to sum of PD. So the EMF is V, so this PD must also be V. If we take this second loop here, the EMF is V, the PD here also must be V. And if we take the third loop here, the EMF is V, the PD here must also be V. So that's why we know that all the PDs are the same. Understand? Now for resistors in parallel, there are some so-called shortcuts and that you can use to solve your circuit problems. The first one is, you will notice they say the lowest value resistor carries the greatest proportion of the current. So what it means is like this. If you connect a few of them in parallel, alright, wait, so up to here, So how will the current actually split? If let's say this is considered to be 1 ohm, 1000 ohm, and 100,000 ohm. Okay, so the biggest current will be in here. Alright, so let's call this I1, and this I2, this is I3. So which current will be the biggest? I1. So I1 will be bigger than I2, will be bigger than I3. So the bigger the resistance, the smaller the current. The smaller the current, the smaller the resistance, the bigger the current. You know why? Because the PD here, here, and here must be the same. So therefore, your small resistance, you need a big current. Okay? So it's something like, you know, water flowing. If this pipe is completely clear with a little bit of rubbish only, but this is completely clogged. So the current here, the water will be very slow here, but here will be very fast. So that's the same idea. Okay. Now, second shortcut here, it says the total effective resistance is less than that of the smallest resistor in combination. So what it means is, if I were to find the total resistance of these three, I can guarantee you I will get my total resistance to be smaller than 1 ohm. If all of them are connected in parallel, the total resistance will surely be smaller than the smallest resistance. Do you understand? How do you calculate this resistance? You can use our formula 1 over RT equals 1 over 1 plus 1 over 1000 plus 1 over 100,000. Then you inverse it to get your RT. I guarantee you get less than 1. So that's how you check whether your calculation is correct. You check the resistors in parallel they give you. When you find the total resistance, it has to be smaller than the smallest resistor. Do you understand? Okay. Next one. If there are n similar resistors in parallel, each with resistance R, then the total resistance parallel is R over N. So example, if let's say you have 4 resistors all in parallel, but the good thing is all of them have the same resistance, all 10 ohm. Okay, all of them are 10 ohm. Then I can straight away find the total resistance without having to use our standard formula, which is 1 over RT equals 1 over R1 plus 1 over R2. You don't have to do that. The shortcut is you just take 10 ohm, which is the resistance of one of them, and you divide by number of resistors you have in parallel, which is 4, and you get 2.5 ohm. Okay, this is a shortcut. Of course, you can still use the long way, but this is way faster. Alright, but it only works if all of them have the same value. Okay? Right, the fourth rule here is, if all the resistors in parallel can be represented with a single resistor, a single equivalent resistor, then the PD across each parallel resistor equals to PD across a single equivalent resistor. So what does it mean now? Now, if you look at this circuit here, your R1, R2 is in parallel, right? I can actually combine these two to get an equivalent parallel resistance RA. So I can redraw this circuit as this. That means the R4 will remain, R3 will remain, but I substitute these two with a single equivalent resistance, right now. So what I'm trying to say is, if I have combined these two to form a single equivalent resistance, then the PD across this will be equals to the PD across R1 will be equals to the PD across R2. Example, if this is 2 volts, then R1 will be 2 volts, R2 will also be 2 volts. You don't add up the 2 and 2 here, you don't do that. So if this is 2 volts, each of these also 2 volts. Why? Because they're considered to be in parallel, which forms this also in parallel. Do you understand? That's a shortcut. So in conclusion, right, if ever you want to get higher resistance, then you must always connect the resistors in series. But if you want to get a lower resistance, then you must always connect them in parallel. The more resistors you connect in series, the bigger your resistance. But the more resistors you connect in parallel, the smaller your resistance. Alright, that's the general rule.